Hello class, this is the video for section 10.1 and we talk about the correlation between two things. At the end of this section, you should be able to determine the linear relationship between two variables, which we call the bivariate data, and compute the correlation coefficient denoted by the letter R, the lowercase. And this measures the strength of linear association between two variables. And then we conduct a formal test to determine whether there is a linear association between two variables that we in question, naturally. Okay. So let's define correlation. It's a correlation that exists between two variables when the values of one variable are somehow associated with the values of the other variable. Okay, and then correlation could be linear, that would be a straight line, or could be parabolic, like a valley or a mountain. All right, but specifically in this section, we want to look at a simple model, a simple linear correlation, simple correlation, which is linear. Okay, now if it's linear, you know we are talking about something like from the algebra is mx plus b, where m is the what? M is the slope, and then b is the what? The y-intercept. Okay, b is the y-intercept. Just write that int. Okay, so that's what we're going to look at. Now, here are measure of linear correlation coefficient. In some software uses this is same as a Pearson. And you see our diagrams, we call this the scatter plots between the variables. So the first diagram to your right, top right, okay, this one, it has between y and x, and you can look at the pattern. There's a pattern that's like a linear, which is going up, so the slope is positive, and so this is a positive correlation. And then when we measure this is about 0.859. Okay, and then the second to the right on the top row is what is a negative, so that has what a negative correlation, which is quite very strong. Now the bottom left, okay, the correlation is very small. As you can see, the scatter plot doesn't see any pattern fashion in a straight line. Sometimes we say that this is about what? It could be the R is about what? 0. Okay, and then this is the one to your right bottom, right? That looks like it's a parabola, but if you look at it, there's a small linear correlation between the two variables x and y. And so looking at the scatter plot sometimes will not really tell whether there is a linear correlation unless you perform what? A statistical test. Okay, that's why it's important to test linearity between what? Two variables. Okay, so we want to construct the the scatter plot, okay, and we're going to switch to which we did in sections 4.2. Okay, so let's just switch over to the homework and look at just the first part. Okay, we'll do the rest later. So question number 3, it says that we should construct a scatter plot. So I'm going to open this in the StatCrunch. Okay, so let's open that in the StatCrunch. But making sure, want to make sure that we are sharing that screen. Okay, and okay, so here is it. So I go to graphs and pick or scatter plot. And then what's my x variable is the internet users. So x variable is the internet users. And then y is what? Award winners. So we want to know whether there's a relationship between internet users and award winners. Okay, when we considered about six individuals. Okay, so when we compute, here is a scatter plot. Look at how it is. Okay, the pair is very few, so this doesn't really depict, correct linearity between the two or pattern, unless you have a lot of them. But in this case, this is the scatter plot for that. Okay. Now let us go back to our question. And then we'll select the right graph. Okay. Now, as we can see, it looks like this is the first or the second one. Okay. Let's check. I believe it's the. Let me go back and making sure we have the right graph. Okay. That's how it is. Award winners, and then x-axis is what the internet users. So let's go back to our question. That's supposed to be. It looks like this what it is the option A. So let's check that and check it out. Okay, so that's good job. So here we want to just do the scatter plot. We'll come back to this question and complete later when we get to the end of this section. All right. So now let's go back and share our PowerPoint and then continue. So that's a scatter plot. It's always, it is, if you look at it as we did in chapter 2, okay, this is my X. Okay, sorry, this is my X. Let me erase this guy. Okay, and then let's go and pick my pen again. So I can draw, okay, so this form where this is your X variable and that is your Y variable. All right, now that's it, and then you can have the pairs, you can plot the points like that, okay, and then I show you using the scatter plot to StatCrunch to construct the graph. All right, so now what are the properties of the linear correlation coefficient? Which from the diagram, the various scatter plots that I showed you, you can see that first, the property, the value of R is between plus or minus, and the closer it is to the positive one, the stronger positively, and closer to the negative one, the stronger or negative. It is strong, okay? So all values of either variable are converted to a different word scale. The value of R does not change. So if you change all the variables, you convert to a different scale, the R doesn't change. Okay, and then if you also switch the X and Y, okay, to use the R compute is going to be the same. Okay, then the value of R is not affected by the choice of X or Y. Okay, you can change X values and Y values, and the correlation, the linear correlation will not change. The value will not change. Okay. Now, the fourth is that it measures the strength of what linear. R measures the strength of what linear. Okay. Now, sometimes we call R is what the Pearson R or Pearson correlation coefficient. Okay. It is not designed to measure the strength of a relationship that is not linear. So if it is not linear, this doesn't work. So you have to use a different approach. And then R is very sensitive to outliers. When you have outliers, you can change the value of what? The R. And that is why sometimes we handle the outliers by deleting if it's justified. Okay? Now, there's a formula for finding what the correlation coefficient or the Pearson, which is that. And we are going to use StatCrunch to do this same thing. So I'm not going to show you how to do that, but I'm bringing it up that to let you know for your information there is, and then what the symbols, what these mean, are being explained in the next few slides. I think the next two. Okay, your n is the number of pairs of the sample. Then this symbol means what? Donations means what? Summation or the addition. And so if you have this x is the sum of all x like we did, sum of L x squared. You square all the x's and then sum them. And then this is what? Sum of the x and then you square that. Okay, this is like what we did in chapter 3, talking about measures of center and then spread. Okay, and then these are the variables for that. Like I said, we're going to use StatCrunch to compute the R. We will not use the formula. Okay, now using technology, like we said, we can find the correlation coefficient. So here is a data set or a sample that correlates chocolate consumption and the Nobel Prize won. And then we consider just only 5 pairs. Now here is the data. I've told you, you can have a correlation between anything, any two things, like my height and my weight. Okay. This one is a chocolate consumption, and then the Nobel Prize won. And we want to see there's a correlation between this by computing R. You'll be surprised there is. But like you said, correlation is not causative. It's not cause and effect. Okay. So here we are considering just 5 for 5 countries, and then the Nobel Prize is won, the total consumption in some terms. Okay. So let us go to StatCrunch and compute the what correlation coefficient using StatCrunch. Good. So I'm going to open the app. I have entered it already here, making sure that I have sharing that with you. Okay. So here is the variable chocolate is the X, and then the Nobel Prize is what? The Y. And so we're going to calculate the correlation coefficient. So you go to statistics and go to regression and then simple linear. That's all we need. So select that, and then our chocolate is the X variable. So we select that. And then the Nobel Prize one is the Y variable. Okay. So that's all we need for now. Let's compute. And this is our the output. Now the output comes with 2 things. It comes with the scatter plot. If you go to the next page with the best line of best fit, and if you put your cursor, it highlights the equation, the regression line. Okay, the equation of the line of best fit, which we'll talk about more in section 10.2. Okay, so let's go back to our output. Now here is the output. Okay, yeah, there's a couple of things that we can look at it. This is the equation of what the regression equation or the regression line, and this is the R, capital R here is a correlation coefficient. So according to this, the correlation coefficient is what? 0.7995 to 3 decimal places. Okay, and then when we square this value, we get this R squared here. We'll talk about what that means. Now, if you look at the first table, that's a parameter estimate for intercept and then what? The slope. If you look at this is the estimate. Okay, that's a y-intercept, which is the same value here. And then this is the slope of what? Of the line, which is there. Now, in section 2.4, we actually describe the meaning of what? How do you interpret the slope? So the slope is what? A unit rise in what? In the x variable. So for every unit chocolate consumption, the y, the Nobel Prize won is in this case what? 3.664 to 2 decimal places. Okay, now if you go to this table, we can find, okay, this is the slope. In fact, this is the t statistics I'll talk about later. And of course, degrees of freedom is n minus 2. We'll talk about that also later. So here, what that we need is what? This value. To take decimal place is what? 0.795. So let's go back to okay. And so here, the correlation coefficient between the two, R is what? 0.795. Okay, let's making sure we have that correct. Okay, it is 0.795. Perfect. So that is that's the correlation coefficient, right? Now we increase the n. Here n is what? N is 5. If you pick like n equal to what? 23, like if consider 23 countries and then a Nobel Prize won, then look at the chocolate consumption, right? We will be able to see whether there's correlation coefficient and correlation, what do you call it? Linear correlation between them. All right. Now, here's an informal test that we did in section 2.4. Okay, we can use the table or find a p-value. Okay, and then alpha is the significance level. So as always, if alpha p-value is less than alpha, we have evidence to support the claim. In other words, we reject what? HO. Now, if it is p-value is of course greater, then we do not. Okay, we do not reject HO. All right. Now, in this informal test, this is what we use. We use a table. That's a correlation that gives the critical values, table A5. Okay, we use that. I'm going to show that table in a minute. But this is the table that I'm talking about. Okay, here's a table that we use this in section 2.4, finding the if you know n is what, for our example, n was 5. And so the critical value at alpha 5 equal to 5% is plus or minus 0.878. Okay, if a alpha is what? 0.01, then that is going to be what? 0.959 plus or minus. This will be your critical values. Okay, so we'll use this again. Okay, so there's a correlation. If you take the absolute value of so because remember the R could be negative. You take the absolute value and it's greater than or equal to critical value, then we conclude that there is sufficient evidence to support the claim. Otherwise, we don't. There's no correlation. In other words, we can use this chart here. Okay. And so for our sample that we looked at, okay, we computed, we just want to consider in this case, this sample, the R, the correlation coefficient is what? It's 0.805. Now we got 0.7, what do you call it, 795. Okay. So for the critical values, when we look at it, it was 8 point. Let's go back and check that, making sure we got that right. Okay. N is 5, so 0.878. Okay. So let's go back and to that. So if you want to decide whether there's correlation there, the critical values in this case is what? 0.878, and this side R is what? Minus 0.878. Okay, 878. Now, this is my correlation, the coefficient that I calculated. Now, where does this value fall? See that this falls in the middle here. Okay, this value, the 0.795 0.95 falls within these two values for n equal to what? Equal to 5. So you can say that here there is no correlation. Okay, so let's go back. If it's that's at 5%, where alpha is what? 0.05 in this case. All right, so let's go back. Our R, for example, that we considered, R is was that, n is what? 5. Okay, so that's why we got the all right. So that's how you use this chart. Again, this is a refresher or review from section 2.4. All right. So again, if I use the technology and then I have my R, using the p-value, if it is less than or equal to alpha, I will reject the null hypothesis or I support the claim. Okay, and then if it is greater, I do not support the claim. So same as we have been doing in what chapter 8. Okay. Now the question is that we call something the coefficient of determination. Now, if I have my regression line, say we're going to use this for that, plus b1 x, so that be consistent with this section 10.2. This is your y-intercept. And then the b1 is my slope, okay? So the question is that how useful, okay, how useful is this this equation or this regression? We call the regression line. Okay, how useful it is? Well, I determined that by what? Calculating what? R squared. So R squared tells me how much of the y is explained by the x. Okay, it's a proportion of the variation in y that is explained by the linear relationship between what? The x and then what? And y. Okay, so here comes our example where we increase the number of what? The chocolate, the pair of chocolate and what? Nobel Prize there. So n is what? 23. Okay, so we're going to calculate the R, which we got 0.801. So let me go back and share my screen. Okay, so I'm going to open that. So here's the data set. Okay, now this data, I'm making sure I have that. I'm showing you this. This data, we have for 23 countries, and they look at what the consumption of what chocolate, and then the Nobel Prizes what won. Okay, if you look at the U.S. consume 5.3 million tons of chocolate, and then Nobel Prizes were 10.8. That Nobel Prize. So we want to see whether a relationship between this by calculating the R. Okay, so we go to our statistics and then regression, simple linear. Okay, my x variable is what? The chocolate, and then my y is what? The Nobel Prize. Then say compute. Okay, now what is my correlation coefficient? You see it's 0.8006. So to 3 decimal places will be what? 0.801. Okay, so you see where the R, the 0.801 is coming from. Yeah. So now, if I continue this, right, I want to see from my PowerPoint, okay, how much of this, okay, is explained by what? how much of the Nobel Prizes won is explained by the chocolate consumption. Okay, we calculate the R squared. Okay, so the answer is just to calculate the R squared, which shows the utility. Like I said, the how useful is a regression line. And then if you square this value, you get that. So what does that mean? It means what? 64% of Nobel Prize is explained by what? Chocolate consumption. I don't know whether that makes sense or not, but according to this model, that's what it's telling us. But that's why sometimes we have to use our common sense. How does chocolate consumption correlate with, Nobel Prizes won? All right. So we interpret this by saying that 64% of the variation in numbers of Nobel, prizes can be explained by the linear relationship between the chocolate consumption and number of Nobel prizes. This implies that about 36 of the what? Of the variation, the number of Nobel laureates cannot be explained by rates of what? Chocolate consumption. So again, correlation is not what? Cause and what? Effects. So remember that it's not causative. Okay. Now, this is what we're talking about. It's not causative. That means that if I have these 23 pairs, right, and then this is R squared is calculated, we know that we use common sense when interpreting the results. Clearly, it would be absurd to think that eating more chocolate will help you win the Nobel Prize. Right? So you got to be careful how you interpret. Sometimes we use common sense and statistics. Okay. All right. So these are some of the common errors that we assume that correlation implies what? Causative. That is cause and effect. And then using the data based on what? Averages. Okay. And then ignoring the possibility of what? A nonlinear relationship. So don't use this is what? Linear relationship. So if something is non-linear, then we don't use this procedure that we are talking about. Okay, so here comes the formal test for talking about the correlation coefficient. Now, remember the R, if you can say that this is a sample, okay, it's a sample correlation, sample R, or you can say this is a statistic has been, if you are consistent with the rest, it's a statistic. It's based on sample. And then the rho is RHO. The rho is what? The parameter. And so we use the R to estimate what? The rho. And so if I say that rho equals 0, it's like saying R is 0 means that there's no correlation. That's your null hypothesis. And then your alternative is not equal to. So this makes it what? A two-tailed test. This is a two-tailed test. A two-tailed test. Okay. Now, what is a test statistic? It's given by this formula. And now this formula is the same as R, as I showed you in class, n minus 2 divided by the square root of what? 1 minus R squared. Now the degrees of freedom, in this case, your degrees of freedom is what? N minus 2. So you can calculate the test statistic and get your p-value, okay? If p-value is less or equal to alpha, you reject what? HO. So meaning that if you reject HO means that there is what? There is what? Correlation. Because remember your H1 is what? The rho, sorry. Each one is not what equal to 0. Now that means we can have a one tail, a right tail, or a left tail. Okay, so your row is not P, this is row, not P. All right. So we're going to consider these examples. We'll finish up the exercise 3 and then also do another example. Now, before I go there, let me also mention that we can also test the claim about the left tail or the right tail, as I mentioned earlier. Okay, so I will not come back to this this slide. Okay, so let's go to do some examples, and that will be the end of this section or this video. Okay, so let's go back. So let's start with the question 3 that we started. We did a okay. So let's go back to right. Then part B, if you remember, we had this. So I'm going to just let me open this in the StatCrunch so that, or I may have it here. Okay. Now let's open this and start calculate the correlation coefficient again. Okay. It's my StatCrunch. All right, so here is the StatCrunch. Okay. And then we go to statistics and then regression, and then linear, and then this is what the internet uses, and Y is the award winners. So let's compute that. So let's make this bigger. Okay, so my linear regression equation is this one right here. Okay, and then this is my R, sample size is here, and that is my R. We got 0.795. Okay, what is my test statistic? Okay, the T is given by this value right here, and then my p-value is that. Okay, p-value is this one. Okay, or if you look at the model, this is the same p-value. Forget about any other numbers there for now. So p-value and then test statistics is that. Okay, and then my scatter plot with the line of best fit is here. So let's go back and finish up, enter the values and see if we got that right. Okay. So the correlation coefficient that we calculated from this is, I believe, is the same one. If it's not, let's be 0.795. Okay. And then what is our now hypothesis? Rho is equal to what? 0. Okay, is equal to 0. And not equal to, that is your what? That's your alternative. Okay. And then you go to what's your test statistic from the output that we got. Okay. From the output we got, it is what? 2.625. If you say to 3 decimal places. Okay, if it's to 3 decimal places, 2.625. Okay, 2.62. Okay, 2.625 or 2.624 if it's the 2 decimal places. So let's go and enter that. So 2 decimal places, so that's 2.662. Okay, what's the p-value? Okay, p-value as we calculated is 0.05885. So to 3 decimal places will be 0.059. Okay, so let's go back, making sure we're sharing that. All right. So that is 0.059 to 3 decimal places. Okay. And so look at this. My alpha is 5%, and this is greater. Okay, it is greater than what? 5. And so we say that there is not sufficient evidence, so we don't reject sufficient evidence to that because this is greater than what? The significance level. Okay, so the correlation coefficient, the p-value for that is was greater than that, so there's no sufficient evidence to conclude that it is what there's linear relationship between the two. Okay, and here is example. Let's go to question number 2. Okay, question number 2. Okay. So here's a question. It said, listed below are amounts of court income and salaries paid to the town justices. All amounts are in what? Thousands of dollars. Construct a scatter plot, find the value of the R, and find the p-value using alpha equals what? 0.05. Okay. Is there sufficient evidence to conclude that there is a linear correlation between the two? So here is a data set talks about the court income and then justice was salary. And so if you look at this, there's a kind of pattern that if the court income is going up, it looks like the justice salary also goes up. So we want to see if there's a correlation coefficient or the correlation between the two or the linear relationship between the two. Okay. So let's open this in StatCrunch. Making sure that I'm sharing that screen with you so you can see what I'm doing. Okay, so we go to statistics and go to regression and simple linear. Okay, my X is the first variable, that's a court income. And then Y is the what? The justice salary. And say, let's compute that. All right. If I compute this, look at this, this is my scatter plot right there. Okay, justice income, Y axis, court income is what? The X axis. Right? Now, let us make this bigger. Now, what is my test statistic? Okay, which is that same value that we calculated. Okay, my correlation coefficient is that. Okay. So to 3 decimal places is what? 0.845. Okay, 0.845. Sorry, this is for 0.8449. So if we compare it to this one, that would be 0.850. All right. Now n is sample size is what? 9. 2 degrees of freedom. That is why the degrees of freedom is what? Is 7. Okay, my p-value is this. Okay, the p-value is given as that. All right. Okay, this is my test statistic. That's a t, which is given by the formula that I showed you, and I'll show you why we got this. So let's go back and share that. Okay, so I have our You have to, our null hypothesis is what? It is equal to 0. Alternative that it is not, so that's it, C. And then our scatter plot, as we did, it looks like the A. The A is the better option. That's the one. Okay. And then what is our R? To 3 decimal places, we said this is what? It was 0.850. Okay. 850. Then what's our test statistic? Okay, let's go to show the test statistic again, which is that. So the test statistic is what? 4.263. So if you choose decimal places, that's 4.26. Okay, to 3 decimal places, that's be 4.263. So 4.263. Okay, and we got that. Now, what is the p-value? Same from the same output, because what? The p-value is 0.0037. Okay, to 3 decimal places will be 0.0014. Okay, so that will be 0.0014. Okay, so now the p-value 0.004 is less than alpha. So we say that it is less than the significance level, which is what? 0.05. So there is sufficient evidence that this is what? There's a correlation coefficient. There's a linear relationship between them. So what does it tell us? Okay, it appears that that the justice profit the same despite the amount of what the fines that there's a court income. B, it does appear that justice might profit by levying larger what fines. Okay, and then it does appear, C, it does appear that justice might profit by issuing what smaller fines. Of course, from what we said, there's a correlation between the two. There's a linear relationship between. That means that, and it's what? It is positive, meaning as the court income increases, the justice salary also increases. And so B will be the better option. Okay, so now let me show you how to use a formula to get the same test statistic, which is what? 4.263 that we got. Okay, where our R is 0.850. Okay, so let's share my whiteboard with you, and then we'll use a formula to calculate that. Okay, so here your N is 9. So degrees of freedom is N minus 2, which is 7. Okay, the T statistic is given by R, okay, which is the same as the square root of 1 minus R squared over N minus 2. Now we said this is the same as R times the square root of N minus 2 divided by the square root of what? 1 minus R squared. Now what was R? R is what? 0.850. Okay, so we have 8.850 times the square root of what? 9 minus 2 divided by the square root of 1 minus 0.850 squared. Okay, now if we evaluate this should be about the same. So I'm going to use my calculator. 0.85 times the square root of 7, okay, divided by the square root of 1 minus 0.85 squared. Okay, exactly the same. This is what I got 4.2691. Okay, so to take decimal places will be that. Okay, so that's how we got it from the same value that we got from using the StatCrunch. And that actually brings me to the end of this section. I hope this is helpful. I'll see you next time. Take care.